Imagine waking up, you open your eyes and instead of your bedroom ceiling, you see a dusty, rust-colored sky. The ground beneath you is frozen. The air, if you can even call it that, would kill you in seconds. No trees, no oceans, no birds. Welcome to Mars, the next great frontier of human exploration. But could you really survive there? And here is a question. If you could bring only one thing from Earth to Mars to help you survive, what would it be? Let me know in the comments. I will pin the most creative answer. Now let's begin. Let's start with something that sounds almost poetic, but is actually one of the most important facts in planetary science. Mars used to be different. A very long time ago, we are talking roughly 3.5 to 4 billion years ago, Mars may have looked a little bit like Earth. There is solid geological evidence, gathered by rovers like Curiosity and Perseverance, that liquid water once flowed across its surface. There were rivers, there were lakes, there may even have been an ocean covering the northern hemisphere, stretching across millions of square kilometers. Think about that. The same barren, frozen world we study today may have once had water lapping against ancient shores. Scientists looking at data from NASA's MAVEN mission, that stands for Mars Atmosphere and Volatile Evolution, discovered that Mars lost most of its atmosphere over billions of years. The sun didn't just warm Mars, it stripped it. Piece by piece, particle by particle, the solar wind tore away the Martian atmosphere because Mars lacks something Earth has that we often take completely for granted, a global magnetic field. Here on Earth, deep inside our planet, molten iron churns and flows, generating a massive magnetic field that wraps around the entire planet like an invisible shield. This magnetosphere deflects the most dangerous particles the sun throws at us. It's the reason Earth kept its atmosphere. It's the reason we still have liquid oceans and a sky full of breathable air. Mars lost its magnetic field a very long time ago. Scientists believe the planet's core cooled and solidified earlier than Earth's did. Without that churning molten iron, the magnetic dynamo switched off. And without that protection, the solar wind went to work on the Martian atmosphere for billions of years, slowly eroding it until what you have left is barely there at all. Today, the atmospheric pressure on the surface of Mars is roughly 0.6% of what it is on Earth's surface. Not 60%, not 6%, 0.6%. To put that into terms you can feel, the atmospheric pressure on Mars is roughly equivalent to what you would experience at about 35 kilometers above Earth's surface. That is far above where any commercial airplane flies. That is in the stratosphere, approaching the edge of space. Standing on the surface of Mars without a pressurized suit, your blood would literally begin to boil. Not because it's hot, but because the pressure is so low that the boiling point of liquids drops dramatically. It's called ebullition, and it is as unpleasant as it sounds. But we haven't even gotten to the cold yet. The average temperature on Mars is around -60 degrees Celsius. That is -76 degrees Fahrenheit. For comparison, the coldest temperature ever recorded on Earth's surface was -89.2 degrees Celsius, recorded at the Soviet Vostok station in Antarctica in 1983. Mars averages colder than one of the most extreme places on our entire planet, and that's the average. Near the poles in winter, temperatures can drop to -125 degrees Celsius. The thin atmosphere provides almost no insulation whatsoever, meaning heat radiates away from the surface incredibly quickly once the sun goes down. Now here is something worth stopping on for a moment, because it really illustrates just how different Mars is from anywhere we have ever been as a species. Every human being who has ever lived, every explorer, every sailor, every mountaineer who pushed into the harshest environments on Earth, they were still on Earth. Antarctica is brutal, but you can breathe the air. The summit of Mount Everest is deadly, but with enough oxygen, people make it. The deepest oceans are crushing and lightless, but humans have reached the bottom in submersibles. We have never sent a living person to a place where the air itself is the wrong substance, where breathing unfiltered is not just uncomfortable, it is instant death, where the pressure alone would cause your body to fall apart within seconds. Mars's atmosphere is about 95% carbon dioxide. The remaining 5% is a mix of nitrogen, argon, and tiny traces of other gases. Oxygen makes up less than 1/5 of 1% of the Martian atmosphere. You would not have enough time to take a single meaningful breath. The Mars Oxygen In Situ Resource Utilization Experiment, called MOXIE, was a small device aboard the Perseverance rover, designed specifically to test whether we could generate breathable oxygen on Mars by splitting CO2 molecules into oxygen and carbon monoxide. And it worked. Between 2021 and 2023, MOXIE successfully produced oxygen in multiple test runs, demonstrating that the technology is real and viable. That is a genuine, exciting breakthrough, but MOXIE was a small proof-of-concept device. Scaling that up to produce enough oxygen to support a human crew continuously, that is an engineering challenge of staggering proportions. We know the chemistry works. Making it work at human scale, reliably, on another planet is a completely different kind of problem. So before we even talk about food or shelter or getting home, before any of that, the simple act of breathing on Mars requires machinery, power, and flawless engineering running without failure for every minute of every single day you are alive there. That is not a solvable problem that we haven't solved yet. That is a solved problem that we need to scale and trust with human lives. And there is a profound difference between those two things. This is where the scale of what Mars colonization actually means starts to come into focus. When you hear someone talk about moving to Mars, it is easy to imagine something like moving to a new country. Challenging, uncomfortable, maybe even dangerous, but ultimately manageable. The reality is far more extreme than that. Every single resource that keeps you alive on Earth, air, water, warmth, food, protection from radiation, every single one of them would need to be manufactured, engineered, or imported on Mars. Nothing comes free, nothing is guaranteed, and we are only just getting started. There is something on Mars that you cannot see, cannot smell, and cannot feel, at least not right away. It doesn't announce itself, it doesn't roar like a storm or freeze you like the cold. It works quietly, invisibly, and relentlessly, sneaking into your body at the cellular level, rewriting the instructions buried inside your DNA, and slowly, methodically, increasing your risk of cancer, organ damage, and neurological deterioration with every single day you spend on that planet. It is radiation, and it might be the single most underestimated threat that any future Mars astronaut will face. Let's talk about what radiation actually is, because it gets thrown around as a buzzword a lot, without people really understanding what it means for the human body. When scientists talk about the radiation environment on Mars, they are primarily referring to two sources. The first is galactic cosmic rays. These are high-energy particles that come from outside our solar system, produced by supernovae, neutron stars, and other violent events happening in the distant galaxy. They travel at close to the speed of light, and they carry enormous amounts of energy. The second source is solar energetic particles, bursts of charged particles thrown out by the sun during solar flares and coronal mass ejections. On Earth, we are protected from both of these by two things working together. The first is our magnetic field, which deflects a huge portion of these particles before they ever reach the upper atmosphere. The second is our atmosphere itself, a thick blanket of gas that absorbs and scatters the radiation that does make it through. Together, these two shields reduce the radiation dose at Earth's surface to levels that the human body can handle over a lifetime without guaranteed catastrophic consequences. Mars has neither of those shields working properly, no global magnetic field, a tissue paper-thin atmosphere. The result is that the surface of Mars is constantly bathed in radiation levels that would be considered dangerously high by any standard we use here on Earth. The Curiosity rover, which has been operating on Mars since 2012, carries an instrument called the Radiation Assessment Detector, or RAD. This instrument was specifically designed to measure the radiation environment on the Martian surface so that scientists could understand exactly what human explorers would be dealing with. And the data it has sent back is sobering. RAD measured that an astronaut on the surface of Mars would receive a radiation dose of roughly 300 millisieverts over the course of a 520-day mission, and that is just from surface exposure, not counting the journey through deep space to get there, 300 millisieverts. For context, the annual radiation dose limit for radiation workers here on Earth, people who work with nuclear materials or in nuclear power plants, is 50 millisieverts per year. The limit for NASA astronauts over their entire career has historically been set to limit their lifetime excess cancer risk. The numbers coming back from RAD suggest that a round trip to Mars, including surface time, would expose an astronaut to a radiation dose that significantly exceeds the career limits currently set for astronauts in low Earth orbit. And those limits exist because radiation damage is cumulative. Every dose adds to the total. Every day on Mars adds a little more to the biological debt your body is accumulating. But here is where it gets even more complicated. And this is something that doesn't always make it into the popular conversation about Mars missions. Radiation doesn't just increase cancer risk. High-energy particles, particularly the galactic cosmic rays, are capable of passing straight through the walls of a habitat, straight through a spacesuit, and straight through the human skull into the brain. When these particles interact with brain tissue, they can cause what researchers call cognitive impairment, problems with memory, decision-making, attention, and spatial awareness. A study published in the journal Scientific Reports, based on research funded by NASA, found that exposure to cosmic ray-like radiation caused significant impairment in the cognitive function of mice, including problems with anxiety and memory that persisted long after the exposure ended. Now, mice are not humans, but the underlying biology of neurons is similar enough that these findings genuinely concerned the research community. The idea that astronauts might arrive on Mars already experiencing subtle but real cognitive decline from the radiation they absorbed just during the 7-month journey there is not science fiction. It is a documented concern that mission planners have to take seriously. So what are the solutions being explored? There are a few. One approach is to build habitats underground or inside lava tubes, ancient volcanic tunnels that exist on Mars and could provide natural shielding from radiation. Another is to use the Martian soil itself, called regolith, as a shielding material packed around habitat walls. Water is also an excellent radiation shield, so storing water tanks around living quarters could help. Researchers are also looking at pharmacological solutions, drugs or compounds that could help the body repair radiation-induced DNA damage more efficiently. None of these solutions are perfect. None of them eliminate the risk entirely. They reduce it, and in the world of Mars mission planning, reducing risk is the name of the game, because eliminating it completely is simply not on the table. And this is a good moment to pause and just acknowledge something that I think is worth sitting with. The people working on these problems, the engineers, the physicists, the biologists, the mission planners, they are not naive. They know exactly how dangerous Mars is. They have spent careers studying it, and they are still working toward getting humans there, not because they are reckless, but because they believe the scientific and philosophical rewards are worth the extraordinary effort and risk involved. That is a deeply human impulse. That drive to go somewhere no one has gone before, to learn something no one has learned before, it is the same impulse that sent sailors across unknown oceans and climbers up into the death zone above 8,000 meters. We are, at our core, an exploring species. And Mars is the next mountain. Speaking of exploring, if this kind of deep dive into real space science is what you're into, please subscribe to this channel and hit that like button. Every single subscriber genuinely helps this channel grow, and I want to build a community of people who get genuinely excited about this stuff. So if that is you, welcome. You belong here. Now, let's talk about something that sounds almost mundane compared to radiation and freezing temperatures, but which is actually one of the most persistently dangerous aspects of the Martian environment, one that no amount of engineering has fully solved yet. The dust. Mars is a dusty world. Extraordinarily, almost incomprehensibly dusty. The entire planet is covered in a layer of fine reddish-brown dust, iron oxide mostly, which is why Mars looks the color it does from Earth. This dust is not like the dust bunnies under your bed. It is extremely fine, with particles small enough to penetrate almost any filtration system and remain suspended in the atmosphere for weeks or months at a time. We know this from direct observation. Global dust storms on Mars are a documented phenomenon. In 2018, a global dust storm engulfed the entire planet for several months, and it was this storm that ended the life of NASA's Opportunity rover, which had been operating on the Martian surface for an incredible 14 years and 217 days. Opportunity relied on solar panels for power. When the dust blotted out the sun so completely that solar energy became insufficient, the rover's batteries drained and the connection was lost. NASA declared the mission over in February of 2019 after a final message from the rover that some people interpreted as heartbreaking, a status report indicating the rover was low on power and that the sky had gone dark. Now imagine that dust storm with human beings inside a habitat on the surface. A global dust storm could last months. If your power system relies even partially on solar panels, and most proposed Mars surface systems do include solar as part of their power strategy, a prolonged dust event could put your entire energy supply at risk. And on Mars, losing power is not an inconvenience, it is a death sentence. Your oxygen generation stops, your heating stops. The temperature inside your habitat begins dropping toward the ambient Martian temperature, which, as we already established, is cold enough to freeze you solid in a matter of hours. The dust itself also poses a direct health risk, one that researchers are actively studying. Martian regolith contains perchlorates, chemical compounds that are toxic to the human thyroid and can disrupt hormone function with prolonged exposure. Perchlorates were first detected in Martian soil by NASA's Phoenix lander in 2008, and subsequent missions have confirmed that they are widespread across the Martian surface. If dust gets inside a habitat, if it gets on equipment, if astronauts track it in on their suits, the contamination risk from perchlorates is real and chronic. There is also the mechanical problem. Fine dust getting into machinery, seals, joints, and air filtration systems can cause failures. The Mars exploration rovers, Spirit and Opportunity, both experienced dust accumulation on their solar panels that reduced their power output over time. Spirit eventually got stuck in soft soil and couldn't reorient its panels toward the sun, which ultimately led to its end. Opportunity cleaned up nicely after wind events that happened to blow dust off its panels, but that was luck. You cannot build a life support system on luck. The engineering solutions being proposed for dust management include electrostatic dust removal systems, essentially using electric fields to repel dust particles from surfaces, better filtration, pressurized airlocks with dust removal protocols, and surface coatings that resist dust adhesion. Again, real progress is being made. But each solution introduces new complexity, new potential failure points, and new things that can go wrong at exactly the wrong moment. And this is the pattern you will notice throughout everything we discuss today. Mars does not have one problem. It has dozens of interconnected problems, each one serious on its own, and all of them layered on top of each other in a way that multiplies the challenge exponentially. Think about it like this. On Earth, if your heating system fails in the middle of winter, it's a serious problem, but you can put on more clothes, light a fire, call a neighbor, drive to a shelter. There are redundancies built into the environment itself. On Mars, if your heating system fails, there is no backup in the environment. There is no neighbor. There is no natural warmth to borrow. The planet is not neutral toward you. It is actively hostile all the time in every direction. This is what makes Mars fundamentally different from any environment humans have ever tried to survive in. We evolved on a planet that, for all its dangers, was built for life, or rather, life evolved to fit it, which amounts to the same thing. Our bodies are perfectly calibrated for Earth's gravity, Earth's atmospheric pressure, Earth's temperature range, Earth's radiation environment. Every single one of those calibrations is wrong for Mars. Every single one needs to be compensated for artificially, mechanically, chemically, every minute of every day. The human body is not a machine that can be simply reprogrammed. It is billions of years of evolutionary history written in flesh and blood, and that history was written entirely on one planet. Your body is lying to you right now, and you don't even know it, not in a harmful way, not yet. But every single moment of every single day, your body is making thousands of tiny adjustments, sending signals, calibrating systems, compensating for forces it has learned to expect over a lifetime of living on Earth. Your heart pumps with a certain pressure because it has to push blood upward against Earth's gravity. Your bones maintain a certain density because they are constantly bearing a certain amount of weight. Your muscles stay at a certain level of readiness because moving through Earth's gravitational field requires a certain amount of continuous effort. All of that is calibrated beautifully, precisely, automatically for one specific gravitational environment, one planet, one number, 9.8 meters per second squared. That is the gravitational acceleration at Earth's surface. Your entire physiology is built around it. And the moment you step onto the surface of Mars, that number changes. Mars has a gravitational pull of about 3.72 meters per second squared. That is roughly 38% of what you experience on Earth. Not zero gravity. That is a common misconception. Mars has gravity. You would not float around. You would walk, more or less. You would feel lighter. Objects would fall more slowly. Jumping would send you higher. It sounds wonderful, honestly, like a permanent trampoline park. But here is what that lower gravity does to your body over weeks, months, and years. And this is where the science gets both fascinating and genuinely alarming. The most well-documented effect of reduced gravity on the human body comes not from Mars, because no human has been there, but from long-duration missions aboard the International Space Station, where astronauts experience microgravity, essentially zero gravity, for 6 months, 12 months, and in some cases even longer. The data collected from these missions is some of the most valuable physiological research ever conducted, and it gives us our clearest window into what reduced gravity does to human biology. The first thing that goes is bone density. In microgravity, the body interprets the lack of mechanical stress on the skeleton as a signal that it no longer needs to maintain as much bone mass. The process of bone remodeling, which is constantly happening in your body right now, with old bone being broken down and new bone being built, shifts out of balance. Breakdown outpaces rebuilding, and the result is that astronauts on long-duration missions lose bone density at a rate of roughly 1 to 2% per month in the most affected areas, particularly the lower spine, hips and legs, 1 to 2% per month. For comparison, post-menopausal women who experience some of the most significant bone density loss of any group on Earth lose about 1 to 2% per year. Astronauts in microgravity can lose that much in a single month. Now Mars' gravity is not zero, it is 38% of Earth's. So the bone loss would not be as extreme as what happens in full microgravity aboard the space station, but it would still happen because 38% of Earth's gravity is still not enough mechanical loading to maintain a healthy skeleton over the long term. Researchers estimate that on Mars, bone loss would occur more slowly than on the ISS, but it would still be significant, and over the course of a year, it could leave an astronaut with a skeleton meaningfully weaker than the one they arrived with. A weaker skeleton means a higher risk of fractures, and a fracture on Mars is not something you can simply go to a hospital for. The nearest hospital is, at minimum, several months away by spacecraft, depending on where the planets are in their orbits. A serious bone fracture in a remote Mars habitat could be life-threatening not because of the fracture itself, but because of the cascading consequences: inability to perform critical tasks, infection risk, the psychological weight of being severely injured on a world with no emergency services. But bone density is just the beginning. Muscle mass follows a similar pattern. Without the constant low-level effort of moving through Earth's gravity, muscles atrophy, they shrink, they weaken. Astronauts returning from long-duration ISS missions often cannot walk unassisted immediately upon return to Earth. Their leg muscles, their core muscles, their postural muscles, all of them have weakened during their time in space, and rehabilitation can take weeks to months. Again, Mars gravity would slow this process compared to full microgravity, but it would not stop it. Then there is the cardiovascular system. Your heart is a pump, and like any pump, it is sized and tuned for a specific load. On Earth, your heart has to push blood upward against gravity to reach your brain and upper body. In lower gravity, that effort decreases. The heart, sensing a reduced workload, begins to adapt, and not in a good way. It can actually shrink slightly in size and reduce its pumping capacity. Fluid distribution in the body changes as well. Without gravity pulling fluid down toward the legs, fluid shifts upward toward the head and chest. This is why astronauts often look puffy-faced in photos from the ISS. It is not just lighting. Their faces are genuinely more fluid-filled because gravity is not pulling fluid down to their lower body the way it does on Earth. This fluid shift causes increased intracranial pressure inside the skull. And this is where one of the most alarming and relatively recent discoveries about long-duration spaceflight comes in. Researchers analyzing MRI scans of astronauts before and after long missions discovered something unexpected and deeply concerning. Extended exposure to microgravity causes structural changes to the brain itself. The brain can shift upward inside the skull. The volume of cerebrospinal fluid, the fluid that cushions the brain, changes. And in some cases, the optic nerve, which connects the eye to the brain, becomes compressed or deformed, causing vision problems. This condition is called Spaceflight-Associated Neuroocular Syndrome, or SANS, and it has been documented in a significant percentage of astronauts who spend extended time in microgravity. Some astronauts return from the ISS needing glasses for the first time in their lives. Others experience changes in their color vision or visual acuity. In most cases, the symptoms partially or fully reverse once the astronaut returns to Earth's gravity, but partial reversal is not full reversal, and some changes may be lasting. On Mars, with its partial gravity, the intracranial pressure issue would be less severe than in full microgravity, but less severe does not mean absent. And there is a compounding factor that makes it worse on Mars than on the ISS in one very specific way. The timeline: SS missions typically last 6 months. The longest single mission in history was performed by cosmonaut Valery Polyakov, who spent 437 days aboard the Mir space station, a remarkable and important experiment in long-duration spaceflight. But even that was done with the knowledge that return to Earth was always an option, always relatively near in time and planning. A Mars mission is fundamentally different. Once you leave Earth on a trajectory toward Mars, you are committed. The planets are only aligned favorably for the journey every roughly 26 months, during what is called a launch window. Miss your departure window, and you might be waiting another 2+ years for the next one. And even if everything goes perfectly, a minimum duration Mars surface stay before the return journey is available is estimated at somewhere between 300 days and 500 days, depending on the mission architecture. So your body is not spending 6 months in reduced gravity. It is spending the better part of 2 years in it, including the roughly 7 months getting there and the roughly 7 months getting back, which happen in actual microgravity. And then you add the surface time on Mars in partial gravity. By the time a Mars astronaut returns to Earth, their body will have been navigating non-Earth gravity environments for somewhere between 2 and 3 years. No human being has ever done that. We do not have data for it. We have projections, models, and extrapolations from shorter missions. But the honest scientific answer to what a full Mars mission-length stay in reduced and zero gravity does to the human body is that we do not fully know yet. And that uncertainty is not a small thing. It is central to whether human Mars missions are safe to attempt with current medical knowledge. Now, here is the part I want to make sure lands properly, because it is easy to hear all of this and think, okay, but we will figure it out. We will develop countermeasures. And that is true. Researchers are working on all of it. Exercise regimens on the ISS have significantly improved bone and muscle preservation compared to early space missions. Astronauts aboard the station spend roughly 2 hours a day exercising with specialist disease resistance equipment. Pharmaceutical approaches, including drugs like bisphosphonates that slow bone resorption, are being studied for use in long-duration missions. Artificial gravity concepts, involving rotating spacecraft or habitat modules, are being explored at the design level. Progress is real. Human ingenuity is extraordinary. We should not underestimate it. But here is the honest truth that gets glossed over in a lot of the breathless coverage of Mars missions. Knowing a problem exists and having a working solution deployed and tested at scale are two completely different things. The gap between identifying a physiological challenge and solving it well enough to guarantee a crew's health and safety over a multi-year Mars mission is enormous. And right now, we are somewhere in the middle of crossing that gap. We have not crossed it yet. There is something profound about this challenge that I think is worth pausing on, because it connects to something much bigger than Mars specifically. The human body is not a spacecraft. You cannot upgrade it before a mission and swap in better components afterward. You are working with billions of years of evolutionary engineering that was optimized for one set of conditions, and those conditions do not exist on Mars, in deep space, or anywhere else we are planning to go. The body that evolved to climb trees, chase prey, and survive African savanna winters is the same body we are asking to handle galactic cosmic rays, Martian perchlorates, and the muscle-wasting effects of 1/3 gravity. The distance between those two realities is almost incomprehensible, and yet here we are, seriously planning to cross it. That, to me, is one of the most extraordinary things about being human. Not that we built rockets, not that we landed on the moon, but that this soft, fragile, perfectly Earth-adapted creature, this walking bag of water and calcium and electrical impulses, looks at a planet 60 million kilometers away and says, "I want to go there." I want to understand it. I want to stand on it. That is not recklessness. That is something ancient and beautiful in us. The same thing that drove our ancestors out of Africa and across continents and over oceans. We are a species that moves toward the unknown, and no amount of danger has ever permanently stopped us from doing it. But understanding the danger clearly, honestly, and completely, that is not pessimism. That is the foundation of actually getting there safely, and we are not done with the dangers yet. Not by a long stretch, because everything we have talked about so far, the radiation, the dust, the thin atmosphere, the bone loss, the cardiovascular changes, all of that assumes your hardware is working, your habitat is intact, your life support systems are functioning, your team is healthy and communicating. But what happens when something goes wrong? What happens when a piece of equipment fails, or someone gets sick? Or, and this is the one that mission planners lose sleep over, what happens when the psychological pressure of being impossibly far from home, in a deadly environment, with no way to leave, starts to crack the human mind? That is where we will go now. The psychology of isolation, the mental health crisis that already emerged during simulated Mars missions here on Earth, and why the inside of a habitat might end up being just as dangerous as the outside. Close your eyes for a moment and try to imagine this. You wake up, the same four walls, the same dim artificial lighting, the same recycled air with its faint metallic undertone, the same faces across the breakfast table, the same 3 or 4 or 5 people you have seen every single day for the past 8 months. Outside the small porthole window, the same rust-colored landscape stretches to the horizon in every direction, flat, empty, ancient, utterly indifferent. You cannot go for a walk. Not a real one, not without spending 30 minutes getting into a pressurized suit, checking every seal twice, running through a safety checklist, and then stepping into an environment that will kill you if anything goes wrong. You cannot call your mother and have her pick up on the second ring. The signal delay between Mars and Earth, depending on where the 2 planets are in their orbits, ranges from about 3 minutes to about 22 minutes one way. A conversation is not a conversation. It is an exchange of recorded messages, each one arriving long after the moment it was meant for has already passed. You cannot leave. That is perhaps the most important thing. There is no door that leads somewhere better. There is no airport, no road, no ocean you can sail to reach another place. The next launch window home is months away. The spacecraft that will take you back is not ready yet. You are here, you are staying, and the planet outside has no interest in your comfort, your sanity, or your survival. This is the psychological reality of a Mars mission, and it is one of the most complex, least fully understood, and potentially mission-ending challenges that space agencies are grappling with right now. Let's start with what we already know, because we are not guessing here. We have real data from analog environments, places on Earth that simulate as closely as possible the isolation and confinement of a long-duration space mission. One of the most important experiments ever conducted in this area was the High Seas program, Hawaii Space Exploration Analog and Simulation, run by NASA and the University of Hawaii. In this program, small crews of volunteers lived inside a dome-shaped habitat on the slopes of Mauna Loa, a volcano in Hawaii, for extended periods, up to 1 year, simulating the conditions of a Mars mission as closely as possible on Earth's surface. They wore simulated spacesuits when they went outside. They observed communication delays. They lived in extremely close quarters with a small group of people with no real privacy and no real escape. What researchers found was both illuminating and sobering. Interpersonal conflict was one of the most consistent and significant challenges. In nearly every mission, tensions between crew members became a serious factor in crew functioning. This is not surprising. When you put any group of human beings in a small, confined space for a very long time with no escape and constant high-stakes pressure, friction is inevitable. But on a Mars mission, that friction is not just unpleasant, it can be genuinely dangerous. A crew that is not functioning cohesively, where trust has broken down, where communication has become hostile or withdrawn, is a crew that is less capable of handling emergencies, and on Mars, emergencies will happen. Researchers identified something called the third quarter phenomenon, a pattern observed in isolated, confined environments where morale and crew cohesion tend to hit their lowest point roughly 3/4 of the way through a mission. The initial excitement has long faded. The end is visible but still frustratingly far away. Boredom, fatigue, and interpersonal friction peak around this period. Antarctic winter-over crews experience it. Submarine crews experience it. HISA's crews experienced it. A Mars crew almost certainly would too. But the HISA's findings go even deeper than interpersonal conflict. Researchers documented something they called third quarter phenomenon, alongside another pattern, the gradual development of what is sometimes called cabin fever, or, in more clinical terms, a collection of symptoms including mood disturbances, cognitive slowing, sleep disruption, and a phenomenon called behavioral health degradation. This is the gradual erosion of a person's psychological functioning under prolonged conditions of isolation and confinement, not a dramatic breakdown, but a slow, steady wearing down of the mental and emotional resources a person uses to stay sharp, motivated, and stable. Now think about what happens when that degradation occurs in a crew responsible for maintaining life support systems, conducting scientific research, managing equipment, and making critical safety decisions every single day. A person experiencing even mild cognitive slowing and mood disruption is more likely to make mistakes, more likely to misread a warning indicator, more likely to delay a repair that needs to be done today, more likely to have a conflict with a crewmate at exactly the wrong moment. The margin for error on Mars is essentially zero, and behavioral health degradation chips away at the human capacity to stay within that margin. Then there is the Earth out of view phenomenon, something that astronauts who have traveled beyond low Earth orbit have described and which would be experienced in its most extreme form on a Mars mission. From the surface of Mars, Earth is not even a recognizable sphere. It is a bright dot in the sky, smaller than the Moon appears from Earth, smaller than Venus looks on a clear night. Everything you have ever known, every person you have ever loved, every experience that formed who you are, all of it compressed into a single pale point of light you could cover with the tip of your finger. Apollo astronaut Edgar Mitchell described having a profound, almost mystical experience while looking at Earth from space during the Apollo 14 mission in 1971. A feeling of overwhelming interconnectedness and awe that he spent the rest of his life trying to articulate and understand. That experience of seeing Earth as a fragile, beautiful whole, what the philosopher Frank White later called the overview effect, has been reported by dozens of astronauts and is now a recognized psychological phenomenon. But the overview effect, as powerful and transformative as it is, works both ways. The same perspective that generates awe and wonder can also generate a profound disorienting sense of disconnection, of smallness, of being impossibly, irreversibly far from home. And for a crew on the surface of Mars, that feeling would not be a brief moment during an orbital flight. It would be the permanent reality of their lives for 2 years or more. Psychologists working with space agencies are deeply interested in something called autonomy, the degree to which a crew can make their own decisions without waiting for guidance from Earth. On the ISS, there is a near real-time communication link with mission control. If something goes wrong, you can describe the problem, get advice, and implement a solution all within minutes. Mission controllers on the ground are an active, present part of the crew's daily life and decision-making. On Mars, with a communication delay of up to 44 minutes round trip, that dynamic is completely broken. You cannot call mission control in an emergency and wait 44 minutes for an answer. By the time the answer arrives, the situation has either been resolved or it has killed you. Mars crews will need to be genuinely, deeply autonomous, capable of making critical, medical, technical, and mission-level decisions without real-time support from Earth. This requires not just competence, but a specific kind of psychological resilience and decision-making capacity that is extraordinarily rare and difficult to select for. There is a concept in psychology called locus of control, the degree to which a person feels they have agency over their own circumstances. People with a strong internal locus of control tend to handle adversity better because they believe their actions can affect outcomes. People with a more external locus, who feel that events are controlled by forces outside themselves, tend to struggle more in high-stress, high-uncertainty environments. A Mars mission would challenge even the most internally grounded person's sense of agency, because there are so many variables that no amount of preparation, skill, or willpower can control. A global dust storm doesn't care how capable you are. A micrometeorite doesn't care how well trained you are. A component failure doesn't negotiate. And knowing that your survival depends not just on your own decisions, but on 1,000 pieces of hardware all working correctly simultaneously, is a psychological weight that is difficult to fully simulate on Earth. And then there is the question of grief. What happens if someone on the crew gets seriously ill? What happens if someone dies? The mission planners who work on these scenarios do not like to talk about it publicly, but they think about it constantly because it is not an unrealistic possibility. A crew of 4 to 6 people on a 2-year mission in an environment full of radiation, physical hazards, and complex machinery, the statistical probability that everything goes perfectly is not 100%. It is not close to 100%. How does a small, isolated crew grieve the loss of a crewmate when there is no funeral home, no family to sit with, no community to lean on, and no option to go home? How do they continue functioning, maintaining life support, conducting science, keeping each other alive, while processing a loss of that magnitude? And how does the fact that the body cannot be returned to Earth factor into the psychological experience of those left behind? These are not hypothetical questions being asked by pessimists. They are active areas of research within NASA's Human Research Program and the European Space Agency's equivalent efforts. Because ignoring them does not make them go away. It just means you are unprepared when they arrive. There is also something worth discussing that gets very little attention in mainstream coverage of Mars exploration: the possibility of what researchers call behavioral sink, a catastrophic breakdown of social functioning within a small, isolated group under extreme and prolonged stress. Historical examples from Antarctic expeditions, submarine patrols, and even isolated research stations have documented cases where crew dynamics deteriorated so severely that mission functionality was critically compromised. In most of those cases, rescue or evacuation was at least theoretically possible. On Mars, it would not be. None of this means a Mars mission cannot be crewed by psychologically resilient, brilliantly capable people who manage all of these challenges with grace and professionalism. Many people perform extraordinarily under extreme pressure. The history of exploration is full of them, but selection, training, and crew composition will need to be treated as mission-critical factors with the same seriousness as rocket propulsion or life support engineering. The human mind is as much a piece of mission-critical hardware as any valve or circuit board, and it can fail just as certainly. What strikes me most about all of this, and I want to share this because I think it reframes the whole conversation, is that the psychological challenges of a Mars mission are not weaknesses. They are not flaws in the astronaut candidates or failures of planning. They are the inevitable consequence of asking human beings to do something genuinely unprecedented in the history of our species. No human being has ever been so far from Earth that the planet of their birth was invisible to the naked eye. No human being has ever been in a situation where return home required waiting months for planetary alignment. No human being has ever had to construct a psychologically sustainable life in a place where nothing in the environment, not the air, not the temperature, not the pressure, not the light, not the sound, is natural to their evolved biology. We are, in a very real sense, asking the human mind to go somewhere it has never gone. And the remarkable thing is not that this is difficult. The remarkable thing is that we are seriously, scientifically, methodically preparing to do it anyway, because the alternative, staying here, not going, letting the universe remain unexplored, feels, to a certain kind of human mind, like a kind of surrender, and those are exactly the kind of minds we need for this. But before we can get anyone to Mars psychologically intact, we need to get them there physically, and that 7-month journey through deep space carries its own extraordinary list of hazards that we have not even touched on yet. The transit itself, through the void between worlds, is one of the most dangerous parts of the entire mission. Before you ever set foot on Mars, before you ever see that rust-colored horizon stretching out in front of you, before any of the dangers we have already talked about become your reality, you have to survive the journey there. And the journey is not a short one. Depending on the specific mission architecture and where Earth and Mars are positioned in their orbits relative to each other, the transit time between the two planets using current or near-future propulsion technology is estimated at somewhere between 6 and 9 months. Most mission planning scenarios use roughly 7 months as a working estimate for a one-way trip using a Hohmann transfer orbit, the most fuel-efficient trajectory between two planets. 7 months, 210 days, give or take, traveling through a region of space that is darker, colder, more radiation-soaked, and more isolated than anything human beings have ever experienced. And the spacecraft carrying you there would be, by any reasonable measure, tiny. Think about the largest long-duration human habitat that has ever existed in space. The International Space Station has a pressurized volume of roughly 931 cubic meters, about the interior size of a 6-bedroom house. It took over a decade and dozens of launches to assemble, and it orbits just 400 kilometers above Earth's surface, close enough that a Soyuz capsule can reach it in as little as 3 hours. A Mars transit vehicle would be a fraction of that size, because every kilogram of mass you add to a deep space mission costs an enormous amount in fuel and launch capacity. Current conceptual designs for Mars transit vehicles envision pressurized living spaces of perhaps 200 to 400 cubic meters at the generous end, roughly the interior of a small apartment. For a crew of 4 to 6 people, for 7 months, let that sink in for a moment. 7 months in an apartment-sized metal tube, flying through the void between worlds, with no ability to stop, no ability to turn around, and no ability to call for help in any meaningful time frame. The ISS, for all its isolation, is never more than a few hours from Earth. A Mars transit crew would be, after the first few weeks of travel, completely beyond any realistic rescue scenario. If something goes catastrophically wrong in month 4 of a 7-month transit, a structural failure, a life support breakdown, a medical emergency requiring surgery, there is no cavalry coming. There is no cavalry that could get there in time, even if one existed. This changes something fundamental about the psychology and the engineering of the mission. Every system needs redundancy, not because it might fail, but because it will fail eventually. and failure cannot be recovered from through outside assistance. The crew needs medical capability not to stabilize a patient for evacuation, but to provide complete, definitive care for any condition that could arise, from a broken bone to appendicitis to a cardiac event, using only what they brought with them. Let's talk about what the deep space environment actually does to the human body during those 7 months, because this is where the radiation story we discussed a while ago gets significantly more serious. On the Martian surface, at least there is some atmospheric shielding, thin as it is. On the surface, you can build habitats with radiation shielding, use the regolith as protective mass, go underground. During the transit through deep space, you have none of that. You have the walls of your spacecraft, that is it. And the radiation environment between Earth and Mars, in what is called interplanetary space, is considerably more intense than either on Earth or even on the Martian surface. The data we have from the rad instrument aboard the Curiosity rover was collected not just on the Martian surface, but also during the cruise phase of the mission. The 8.5 months Curiosity spent traveling from Earth to Mars inside its spacecraft. The measurements showed that the radiation dose received during the transit was actually higher per day than the dose received on the Martian surface itself. The transit, in terms of radiation exposure, may be more dangerous than the destination. During the transit, the two main radiation threats are still galactic cosmic rays and solar energetic particles, but in deep space, without Earth's magnetosphere providing any protection at all, the exposure is unrelenting. Galactic cosmic rays are particularly difficult to shield against because of their enormous energy. Building walls thick enough to stop them entirely would require so much mass that the spacecraft becomes impossible to launch economically. Current shielding strategies focus on reducing exposure rather than eliminating it, using water tanks, polyethylene panels, and other hydrogen-rich materials that are relatively effective at scattering cosmic radiation. But there is a specific scenario that keeps radiation safety engineers awake at night, and it involves the sun. Solar energetic particle events, sometimes called solar proton events, are bursts of highly energetic particles thrown out by the sun during solar flares and coronal mass ejections. On Earth, these events are largely handled by our magnetosphere. In deep space, they are not. A major solar proton event hitting a lightly shielded transit spacecraft could deliver a radiation dose that causes acute radiation syndrome, the kind of radiation sickness associated with nuclear accidents within hours. Acute radiation syndrome is not a slow, statistical increase in cancer risk. It is an immediate, life-threatening medical emergency. Symptoms include nausea, vomiting, fatigue, and immune system collapse. At high enough doses, it is fatal within days to weeks. Even at non-fatal doses, it causes serious damage to the bone marrow, the gastrointestinal tract, and the immune system that can take months to recover from, if recovery is possible at all, given the limited medical resources aboard a transit spacecraft. The mitigation strategy most often proposed is to build a dedicated storm shelter within the spacecraft, a small, heavily shielded space where the crew can retreat during a solar particle event and ride it out. The shielding in the storm shelter would be denser than the rest of the ship, using materials like polyethylene or water walls, and the idea is that a few hours or days inside this space during a major event would reduce the dose to survivable levels. It is a reasonable engineering solution, but it requires advance warning, enough time to detect the event, assess its severity, and get everyone into the shelter before the particle flux peaks. Space weather forecasting has improved dramatically over the past 2 decades, particularly through missions like NASA's Solar Dynamics Observatory and the Stereo spacecraft, which monitor the sun continuously and provide early warning of major events. But space weather forecasting is not perfect. We cannot always predict how severe an event will be or how quickly it will develop. And some of the most dangerous solar proton events are associated with the fastest, most energetic coronal mass ejections, the ones that give the least warning time. The gap between we detected something and particles are hitting the spacecraft can be as short as tens of minutes for the most energetic events. That is not much time to assemble a crew, confirm everyone is accounted for, seal the shelter, and verify the shielding integrity. And all of this is happening in a spacecraft that has already been in operation for months, with components that have been exposed to the thermal cycling, vibration, and radiation of deep space for the entire duration of the mission. Hardware degrades, seals weaken, electronics accumulate radiation damage. The probability of a system failure increases with every passing day, and the further you are from Earth, the less able you are to do anything about a failure you cannot fix with what you have on board. Now, here is something that I find genuinely extraordinary about this whole picture, and I want to take a moment with it because I think it changes how you see the entire enterprise of deep space exploration. Every probe, every rover, every spacecraft we have ever sent to Mars, every single one of them was launched knowing it might fail. The history of Mars exploration is littered with missions that did not make it. The Soviet Mars program suffered numerous failures throughout the 1960s and 70s. NASA's Mars Observer was lost in 1993. ESA's Beagle 2 lander crashed on the surface in 2003. Japan's Nozomi mission failed to enter Martian orbit in 2003. These were uncrewed missions, and their losses were setbacks, painful, expensive setbacks, but not tragedies in the deepest sense. When you put human beings in that spacecraft, the calculation changes completely. A spacecraft failure is no longer a scientific and financial loss. It is a human catastrophe. The weight of that responsibility, the knowledge that every engineering decision, every quality control choice, every risk assessment has human lives on the other end of it, is something that the people working on these missions carry with them every single day. And yet they go on. They keep designing, keep testing, keep refining, because they believe, and the evidence supports this belief, that it is possible, not easy, not safe in any conventional sense, but possible with enough intelligence, care, and determination applied to the problem consistently over enough time. There is something in that commitment that I find deeply moving, because it reflects a quality in human beings that goes all the way back to the beginning of our story as a species. The refusal to accept that a barrier is permanent just because it has never been crossed before. But let's stay with the transit a moment longer, because there is one more dimension to the journey that doesn't get nearly enough attention, and it connects to something we touched in a profound way. The transit to Mars would be the loneliest journey in human history, not just in terms of physical distance, though the distance is staggering. At its greatest separation, Earth and Mars are about 401 million kilometers apart. But in terms of the felt experience of isolation, of disconnection from everything familiar, the transit would represent a psychological frontier as unexplored as the destination itself. Human beings evolved as intensely social creatures. Our brains are wired for connection, for the sight of familiar faces, the sound of familiar voices, the reassurance that comes from being embedded in a community of people who know and care about us. Everything about our psychology assumes that other human beings are accessible, that help is nearby, that belonging is possible. In the transit between Earth and Mars, belonging is a memory. Your community is the 4 or 5 people in the same metal tube as you, who are experiencing the same stress, the same fear, the same homesickness, and who need just as much support as you do. The signal delay makes Earth feel like a distant dream, messages from home arriving like letters from another century. full of love and context that no longer matches your present moment. Researchers studying long-duration isolation have found that the quality of communication with loved ones on Earth matters enormously to the psychological well-being of isolated individuals. Not just the frequency, the quality. Messages that feel present, responsive, and genuinely connected to what the person is currently experiencing are far more sustaining than messages that feel generic or outdated. But a 22-minute one-way communication delay makes genuine responsiveness structurally impossible. By the time your partner on Earth responds to what you said, your emotional state has moved on. The conversation is always slightly out of sync, slightly behind the moment, like trying to have a meaningful exchange through letters during a war, except the letters take 22 minutes each way instead of weeks. Some researchers have proposed that autonomous artificial intelligence companions, essentially sophisticated AI systems trained to provide social and emotional support, could partially fill the gap left by the communication delay. It is an idea being taken seriously, not dismissed. Because the psychological need is real and the constraint is physical and unavoidable, we are also learning from ISS missions and from the high CIAS analogues that personalization and autonomy within the habitat environment matter more than almost anything else for long-term psychological well-being. The ability to decorate your sleeping space, to choose what you eat within available options, to have some area of your life that feels genuinely yours. These small things have outsized effects on mental health in confined environments. They are not luxuries, they are mission-critical psychological infrastructure. And private communication with Earth, the ability to have a conversation with your family that is genuinely private, not monitored by mission controllers, not subject to review, is something that astronauts on long missions have consistently identified as one of their highest priorities. The feeling of having some part of your inner life that belongs only to you and the people you love, even across the void of space, is central to maintaining psychological integrity. All of this, the radiation, the isolation, the confined space, the hardware stress, the communication delays, the solar weather risks, is what the crew has to survive before they even arrive. And when they do arrive, when that rust-colored planet finally grows from a distant point of light into a world filling the window of their spacecraft, they will have already spent 7 months accumulating radiation damage, muscle loss, bone density reduction, and psychological wear, and then they step out into it, which brings us, finally, to some of the more surprising and less discussed threats waiting on the Martian surface itself. Threats that are not dramatic in the way that radiation or freezing temperatures are dramatic, but which are insidious, persistent, and deeply challenging to solve with current technology. Let's talk about something so fundamental, so basic, so deeply woven into the fabric of being alive that we almost never stop to think about it here on Earth. Lunch right now, somewhere near you, there is food. Maybe in a refrigerator a few steps away, maybe in a cabinet above the counter, maybe in a restaurant down the street, or a market a few minutes' drive away. Food exists in your world in such abundance, with such accessibility, that the real challenge for most people in developed countries is not finding it. It is choosing between too many options. Fresh vegetables, packaged meals, frozen dinners, takeout, delivery, the entire infrastructure of modern food production, distribution, and storage exists silently around you, so reliable and so invisible that you can forget it is there at all. On Mars, none of that exists, not a single piece of it, and building something that even remotely approximates it, something capable of keeping 4 to 6 human beings adequately nourished for 2 or more years on a planet with no agriculture, no soil organisms, no rainfall, and no grocery supply chain, is one of the most complex and underappreciated challenges in the entire Mars mission picture. Let's start with what we know about human nutritional needs, because this is the foundation of everything. An adult human being engaged in the kind of physically demanding work a Mars astronaut would be doing, maintaining equipment, conducting surface expeditions, operating scientific instruments, performing habitat maintenance, burns somewhere between 2,500 and 3,500 calories per day, depending on body size and activity level. Over the course of a 500-day surface mission, a crew of 4 people would need to consume somewhere in the neighborhood of 5 to 7 million calories in total. That is before you factor in the transit. Every calorie has to come from somewhere, and on Mars the options are severely limited. The first and most obvious approach is to bring food from Earth. Pack enough shelf-stable, calorie-dense, nutritionally complete food to last the entire mission and ship it ahead of time. This is actually the baseline assumption for the earliest Mars missions. Crews would arrive at a habitat that had been pre-stocked with supplies sent in prior unmanned cargo missions. NASA and other agencies have done extensive work on developing food systems for long-duration spaceflight, and the technology for creating shelf-stable, nutritionally adequate food that lasts for years without refrigeration is genuinely impressive. But here is the problem with relying entirely on pre-shipped food. And it is a big one. Every kilogram of cargo sent to Mars costs an enormous amount of money and energy. Estimates vary depending on the mission architecture, but current rough figures suggest that getting 1 kilogram of payload to the Martian surface costs somewhere in the range of hundreds of thousands to potentially millions of dollars, depending on how you account for the full mission cost. Food is not calorie-dense enough, relative to its mass, to be shipped entirely from Earth for a long-duration mission without the costs becoming completely impractical. More importantly, and this is the vulnerability that mission planners worry about most, a crew that is entirely dependent on pre-shipped food from Earth has zero resilience if something goes wrong with the supply. If a cargo mission fails, or if the food stores are damaged, contaminated, or run out faster than anticipated, there is no backup, there is no local source, there is nothing to fall back on. The crew starves, or they cut rations so severely that their health begins to deteriorate, which, given everything else their bodies are already dealing with, could cascade into a crisis very quickly. The solution that has received the most serious scientific attention over the past decade is growing food on Mars, and this is one of the areas where real, genuinely exciting science has been done, though the challenges remaining are immense. The concept of growing food in space is not new. Aboard the International Space Station, astronauts have successfully grown and eaten several varieties of leafy green vegetables, lettuce, kale, radishes, mustard greens, using a system called Veggie, which uses LED lighting tuned to specific wavelengths that plants use most efficiently for photosynthesis. These experiments demonstrated that plants can grow in microgravity, that the food produced is safe to eat, and that the psychological benefit to crew members of tending living plants and eating fresh food was significant and measurable. In 2015, ISS astronauts ate the first food grown and harvested entirely in space, red romaine lettuce, and described it as one of the best meals they had during their mission. On Mars, growing food would require solving several additional layers of complexity beyond what the ISS experiments demonstrated. First, there is the light. Mars receives about 43% of the solar energy that Earth does because it is farther from the Sun. That is actually not terrible for plant growth. Plants on Earth use only a fraction of available sunlight anyway, and supplemental LED lighting could compensate for the deficit. But supplemental lighting requires power, and power on Mars is a precious and finite resource. Then there is the soil. Martian regolith, the loose surface material covering most of the planet, is not soil in any meaningful agricultural sense. Real soil is a living ecosystem, teeming with bacteria, fungi, earthworms, and organic matter accumulated over millions of years of biological activity. Martian regolith is sterile, chemically hostile, and as we discussed earlier, laced with perchlorates that are toxic to plants at sufficient concentrations. You cannot simply dig up some Martian dirt and plant seeds in it. Researchers have experimented with treating simulated Martian regolith, mixing it with organic matter, washing out the perchlorates chemically, adding bacterial cultures and nutrients to create a growth medium that plants can actually survive in. Some of these experiments have shown promising results. Scientists at Wageningen University in the Netherlands demonstrated in 2019 that several crops including tomatoes, peas, and radishes could grow in regolith simulant that had been amended with organic material. The crops looked healthy. Some of them produced viable seeds, but simulated Martian regolith is not actual Martian regolith. The simulants used in these experiments are approximations, mixes of earth materials designed to mimic the chemical composition of Martian soil, but they may not perfectly replicate all of its properties. The only way to truly know whether crops can grow in actual Martian soil is to try it on Mars, with seeds and equipment sent specifically for that purpose. NASA's Perseverance rover is not equipped to test plant growth. That was not part of its science mission. But future missions specifically designed to test in-situ resource utilization, including food production, are being planned. The challenge is that planning and executing are separated by years to decades of development, testing, funding decisions, and mission architecture choices. Even if food production on Mars becomes viable, the crops that can realistically be grown in a pressurized, artificially lit, carefully controlled habitat are limited. Calorie-dense staples like wheat, rice, and potatoes are the most frequently discussed candidates. Potatoes in particular have attracted attention not just because of a certain popular novel and film, but because they are genuinely one of the most calorie-efficient crops you can grow per square meter of growing space, and they can be grown in relatively poor soil conditions with the right amendments. But growing enough calories to sustain a crew entirely through local food production would require a growing area of hundreds of square meters, a greenhouse or series of greenhouses of significant size, which means significant habitat construction, significant power requirements, significant water use, and significant engineering complexity. And it would require that everything goes right, no crop failures, no equipment failures, no contamination events. For the entire duration of the mission, crop failure on Mars is not a bad harvest season, it is a survival emergency. Which brings us to water, because you cannot grow food without it, you cannot drink without it, and the human body begins to shut down within 3 days of complete water deprivation. Mars does have water. That much is now well established. There is water ice at both polar caps, significant quantities of it, with the North Polar Cap alone estimated to contain enough water ice to cover the entire planet in a shallow ocean about 11 meters deep if melted. Subsurface ice has been detected at surprisingly low latitudes by the SHARAD and MARSIS radar instruments aboard Mars Reconnaissance Orbiter and Mars Express. In 2018, a study using MARSIS data announced the detection of what appeared to be a liquid water lake beneath the southern polar ice cap. Though subsequent research has raised questions about the interpretation of that data and whether the radar signature truly represents liquid water or something else entirely, the point is that water exists on Mars, but accessing it and making it usable is enormously complicated. Extracting water from subsurface ice or polar caps requires drilling or mining equipment capable of operating in Martian conditions, low temperatures, low pressure, dust, limited power. The water extracted would need to be purified. Because Martian water sources likely contain dissolved salts, perchlorates, and other contaminants, the purification process requires more equipment, more power, more engineering, and once purified, the water needs to be used extraordinarily efficiently, because on Mars there is no rainfall to replenish what you use, no river to draw from, no well to sink into a water table fed by a living hydrological cycle. Water recycling on a Mars mission would need to be far more efficient than anything currently deployed even on the ISS, where approximately 90 to 93% of water is recycled through the environmental control and life support system. On Mars, you would want to push that figure as close to 100% as physically possible, recovering water from breath condensation, sweat, urine, and all other moisture sources, filtering and purifying it, and returning it to the system continuously. The technology to do this at high efficiency exists and is being improved. But efficiency and reliability over long time periods, in a remote environment with limited spare parts and maintenance capability, are different things from efficiency and reliability in a well-maintained laboratory or aboard the ISS, where resupply missions arrive regularly. And then there is power, the thread that runs through every single other challenge we have discussed. Because without adequate, reliable power, nothing else works. Oxygen generation stops, water recycling stops, heating stops, lighting stops, food production stops, communication stops. Everything that keeps you alive on Mars runs on electricity, and that electricity has to come from somewhere. The two most seriously considered power sources for early Mars surface missions are solar and nuclear. Solar power, using photovoltaic panels to convert sunlight into electricity, is appealing because it is modular, relatively lightweight, and well-understood technology. NASA's Mars InSight lander and the Opportunity and Spirit rovers all used solar power. The Perseverance rover, notably, uses a nuclear power source, a multi-mission radioisotope thermoelectric generator, or MMRTG, which converts the heat from the natural radioactive decay of plutonium-238 into electricity. For a human mission, both sources have significant limitations. Solar power on Mars produces less energy per panel than on Earth because of the reduced solar flux, that 43% figure we mentioned earlier. Dust accumulation on panels reduces output further over time, and during global dust storms, like the one that ended the Opportunity rover's mission, solar power output can drop to nearly nothing for weeks or months at a time. A crew dependent primarily on solar power during a global dust storm is in serious, potentially fatal trouble. Nuclear power, specifically fission reactors rather than the RTGs used on rovers, would provide far more reliable and consistent energy, independent of sunlight and dust. NASA and the Department of Energy have been developing a small fission reactor called Killer Power, which in ground tests has demonstrated the ability to produce 10 kilowatts of electrical power continuously. 10 kilowatts is not a lot by human infrastructure standards. A typical American home uses about 1 to 1.5 kilowatts on average, but it is a meaningful start, and multiple kilopower units could be combined to provide the power levels a crewed habitat would require. The challenge with nuclear power on Mars is not primarily technological, it is regulatory, logistical, and public perception related. Launching a nuclear fission reactor from Earth requires extraordinary safety protocols, international agreements, and public acceptance processes that are complex and time-consuming. The radioactive fuel must be contained safely through launch, including in the event of a launch failure. And operating a nuclear reactor on the Martian surface requires as maintenance and monitoring capability that adds another layer of complexity to an already extraordinarily complex mission. None of these problems are insurmountable, but none of them are solved yet in the fully deployed, human mission-ready sense. And this is the pattern that runs through everything in Mars mission planning. The problems are identified, the approaches are being developed, real progress is being made, but the gap between current capability and mission-ready capability remains significant. Here is what I want you to take from all of this, from the food, the water, the power, because there is a perspective here that goes beyond the technical details. Everything that sustains human life on Earth is provided by the planet itself, freely, as a consequence of billions of years of geological and biological evolution that created an environment perfectly calibrated, or rather, one that life perfectly adapted to for creatures like us. The air is breathable because plants and cyanobacteria spent billions of years filling it with oxygen. The water is accessible because the hydrological cycle continuously purifies and redistributes it. The soil is fertile because countless generations of organisms have lived and died and decomposed in it, enriching it with nutrients and structure. The temperature is livable because our atmosphere traps just enough heat from the sun to keep liquid water stable. None of that happened on Mars. Or if it did, if Mars once had something like it, billions of years ago, it is long gone. What remains is a stripped, cold, ancient world that offers nothing to life without extraordinary effort. To survive on Mars, human beings would need to recreate from scratch, in miniature, the life-sustaining functions that Earth performs effortlessly and automatically. Air, water, food, warmth, pressure, protection from radiation, every single one of those, engineered and maintained by human hands and machines in an environment that is actively working against you. The scale of that undertaking is genuinely humbling, and it makes you look at the planet beneath your feet, this warm, wet, living, breathing world, with a kind of awe that is hard to fully articulate. Earth is not just where we happen to live. It is, as far as we currently know, the only place in the universe where the conditions for complex life assembled themselves naturally, spontaneously, and maintain themselves over billions of years. Every breath you take is a gift from 4 billion years of planetary evolution. Every glass of water you drink is part of a cycle that has been running since before the first fish swam in a Precambrian sea. Mars makes you see that, not by being beautiful, though in its own stark, ancient way it is, but by being everything Earth is not, and yet we want to go. And I think that instinct is right. Because understanding Mars, really understanding it from the inside, with human eyes and human curiosity and human questions, will teach us things about Earth, about life, about ourselves, that we cannot learn any other way. But there is still more standing between us and that understanding than most people realize. Mars will humble you. It will challenge everything you think you know about survival, about resilience, about what it means to be human. The radiation will work silently through your cells. The cold will press against every wall of your habitat. The dust will find every crack. Your bones will slowly weaken. Your mind will ache for a sky that feels familiar, and the planet will offer you nothing, not a single breath, not a single drop of clean water, not a single moment of effortless safety, without an extraordinary fight to earn it. And yet, here we are, a species born on a warm, wet, breathing world, looking up at a rust-colored dot in the night sky and refusing to stop dreaming about standing on it, because that is who we are. We are made of the same stardust as Mars, forged in the same ancient stellar explosions, children of the same universe, and maybe that is exactly why we feel this pull toward it. Not because Mars is easy, but because it is the next question, and we have never, in our entire history as a species, been able to leave a question unanswered. So keep looking up, keep asking, keep wondering. The universe is vast, it is ancient, it is stranger and more beautiful than anything we have fully imagined yet, and we are just getting started.